Hello everybody, I hope you're all doing well. Today we're going to look at a problem on 2D rigid body equilibrium, and this is a problem on what is called as a smooth support or a smooth contact. Okay, so here is the problem. Alright, so I have this bar AB which is pinned on one end and it's resting on a smooth wall at the other end. Okay, so here is the bar. Let me draw it first. So let's say that this is the bar with a slightly increased thickness for this bar, so as to distinguish this from dimensions and so on. Okay, so here is that, and then on one end of this bar I have a pinned support. Okay, so this is the pin support that we have seen in previous problems. Okay, so let me call this end as the end A, and at the other end this bar is in contact with a smooth inclined wall. Okay, so this is a smooth inclined wall, and then we'll see what is the meaning of a smooth wall. I guess essentially the idea is that if you have a smooth surface, then friction is not of any importance here. Okay, so that's the reason why we call it as a smooth wall. And then let me just extend it a little more. Okay, so that I can draw a slope triangle right down there so as to give the angle of this inclined surface. Okay, so the slope triangle is as given to us, and let me do that here. Okay, and this is going to be 1 root 3 and then 2. Okay, and let me call this end of the bar as wall as B, or the end of the bar is B, and there is a force that is acting at the midpoint of this bar. Okay, it's a fairly simple loading situation. Okay, so at the middle of the bar there is a force of magnitude 100 newtons. Okay, and we are told that okay, the distance from point A to where the force is acting is 1 meter, and distance from point where the force is acting to the end of the bar is also 1 meter. Okay, so you're told that the support at A is a pin support. Support at A is a pin support. Then the support at B is a smooth contact. Okay, where smooth implies that no friction. Okay, and then later on, when we actually get to problems on friction, you'll see how this can be handled. Okay, and so what are we supposed to do? We are supposed to find all the support reactions at A and B. Okay, so obtain all the support reactions at A and B. Okay, so this is the problem. So what do? We typically start off by drawing the free body diagram of this entire setup. Okay, and we also typically know that okay, if I have a pin support, then obviously the pin support prevents translation in both the directions but allows me to rotate. Okay, so typically this is how I view the problem. This is how I analyze the problem. I first let's say okay, I'm going to look at the solution. Okay, so here is how I analyze it, and what you'll typically see is that as I analyze this problem, I will draw what is happening at each individual support and then identify okay, how is the support reaction going to be. Okay, so for example, I would say okay, here is the pin support. Okay, I would draw a portion of this beam. I would not draw the entire thing. I would just draw a small portion of this beam. Okay, and then I would say okay, I'm not interested in what's going on at the other end of the beam. I'm just interested in what's going on at where this pin support is acting. And then I will think, okay, does the pin support allow me to translate horizontally? Obviously the answer is no. Does the pin support allow me to translate vertically? Obviously the answer is no. Does the pin allow me to take this bar here, this piece of the bar, and allow me to rotate this bar here? Okay, obviously I am able to do that, right? Because this is almost like taking your hand and then rotating it about the shoulder joint, as we have discussed in some of my previous examples. Okay, so this is allowed, which means that I'm going to have two support reactions. Okay, which are both forces. So two forces, one horizontal and one vertical. Okay, the important thing to understand is this: if a support prevents translation in any particular direction, there is going to be a reaction force in that direction, which means that if a support is preventing translation horizontally, there is a reaction force that way. If there is a support that is preventing translation vertically, there is a reaction force that way, which is why we have these two forces here, horizontal and vertical. Since this support is not preventing rotation, I'm allowed to rotate, at the point A, even though the entire problem itself may not allow me to rotate. If I just look at it from the perspective of just the pin support, I'm allowed to take this body and rotate it about the point A. Okay, so which means that there is a rotation allowed, so there is no reaction moment in this problem. Likewise, I do the same thing at the smooth support. Okay, so I take the smooth support and then I draw it out here. Okay. Okay, and then I'll take this piece of the beam that I had here. Okay, and then I'll just come and draw it here, and then I'll think, okay, what is the smooth support going to do? Look at this. Am I allowed to translate along the direction of the incline? I am definitely allowed to translate along the direction of the incline. There is nothing preventing me from doing that. Am I allowed to translate in a direction that is perpendicular to the incline? Can I dig into the incline? Obviously, I cannot take this bar and then go into the incline, which means that there is something that is preventing me from doing that. Now, think of it also this way: am I allowed to rotate about this point of contact between the beam and the incline? There is nothing preventing me from rotating this beam, right? And when I say rotation, I don't mean a 360-degree rotation. I say that, is there any resistance to any small rotation that I might give to the beam? There is nothing, which means that I'm allowed to rotate. So the only reaction force in the form of a smooth support is a reaction that is perpendicular to the support. Okay, so the smooth support, so there is only one support reaction. Okay, this is a reaction force that is normal to the line of contact. Okay, or this is a support reaction that is perpendicular to the direction of the support. Okay, so this is a support reaction that is perpendicular to the wall at point B. Okay, so if you have a smooth support, typically we call a line of contact. Okay, let's say what is meant by line of contact. So let's say that I have some kind of this wall here, right? And then I have this little piece of the beam. I just draw it here. What is my line of contact? If I draw that line, I'm going to draw this in a different color. Okay, so this line here, which is passing through the contact point, is called as the line of contact. Okay, line of contact. Okay, this is essentially tangent to the contact point, tangent at the contact. Okay, and so if I have a smooth support, the reaction force is going to be perpendicular to the line of contact. Okay, so smooth support, the reaction force is perpendicular to the line of contact. Okay, and in a sense, this is almost the same as having some kind of a roller support here. Okay, so this is the same. I can draw the situation in the following form. Okay, so I can just take that. Let me take this piece of beam here. Okay, then let me say, okay, I have some kind of a roller support here. Let me make sure that this beam is the one that is seen in the front, or I guess I have to not fill it. Okay, so let's say that this is the roller support. Okay, so this is the roller support, and then let's say that, okay, there is some kind of a wall here. Okay, it is the exact same situation that I have just drawn above. Okay, there is no difference here at all. Okay, essentially the line of contact in this situation is going to be this line that I've just drawn right here. Okay, so that is going to be the line of contact. Let me just extend it onto the other side as well, just to show that. Okay, so once again here, this is the line of contact. Okay, what I've just done is, okay, instead of just drawing only the beam contacting the wall, I've drawn a roller right there. Okay, so this is an example of a roller contacting a smooth surface. How many support reactions? I'm still having only one support reaction. Okay, so in this case the roller is contacts the wall. Okay, still only one support reaction perpendicular to the line of contact. Line of contact. Okay, so which means that whether you have a smooth contact, or whether instead of a smooth contact you have a roller attached at the end of the beam and the roller is contacting the wall, it makes no difference to us. The direction of the support reaction is always going to be perpendicular to the wall. Okay, and this is something, or perpendicular to the line of contact. Okay, and this is something that we will make use of in consequent problems as well. All right, so what we have now is that we have a pin at the point A, so I have two support reactions. I have a smooth contact. Because it's a smooth contact, there is no friction. I have one support reaction at the end B. So now I'm ready to draw the free body diagram. Okay, so now let us draw the free body diagram of the bar AB. Okay, and here is the bar AB as we know. And let me draw this slightly thicker. All right, and then I have the pin reactions at A. I can just draw them in the vertical and the horizontal directions. I can choose, as we have seen in previous problems, I can choose what the directions will be. Okay, it does not really matter to me. Okay, so I can call this as A Y, and I will call this as AX. Okay, and then I have this applied force which is acting at the middle of the beam. Okay, so that's a value of 100 newtons. Okay, and then the distances are given to me, and then first of all, before I do anything, I have this smooth contact which I'm just going to draw in the form of this dotted line here. This is the line of contact, right? As we have seen earlier, in this line of contact, the reaction force is going to be perpendicular to this line of contact, as you can see here. Okay, so I'm just going to call this as the contact force at B. So this is going to be called as N suffix B. Okay, this is some kind of a normal contact force. Okay, so NB is the contact or support reaction at B, normal to the wall, normal or perpendicular to the wall. Okay, and then I have this slope triangle that was given to me, so that's something that I'm going to draw as well. Okay, so here is that slope triangle, and this was, I think, 1 root 3 and then 2, and let me call this angle here as the angle theta. Okay, because I'm going to make use of that in a minute. And then of course I have these distances and so on, so let me mark the distances here, of course using dotted lines. Okay, that's 1 meter, As you can see, the loading situation is fairly simple in this problem. In many problems, you might have different other types of loads acting, which is not a big deal. I mean, one can always take care of them. Okay, so let me draw these using dotted lines as well. Once you have the free body diagram, the problem is pretty much done, because there is nothing much to do here. You're just summing forces, you're just summing moments, and then that is the end of the story. Okay, so one thing I want to show here is this. Look at the slope triangle here. I want to take this NB force and then break it into its components. Okay, so here is how I do that. So I want to break the force NB into a component that is acting vertically up, and then I want to break it into a component that is, let me move this guy a little on here. I guess I'm running out of space, but I'm going to draw a force that is the horizontal component of this force NB, right? Which means that for that I need to know what the angle here is, and how do I find that out? Okay, so here is typically what I do. I take this line that I have just drawn, okay, I just extend it here, okay, and then I complete a triangle. I complete this triangle here. Okay, then I realize, okay, if that angle there is theta as I have marked, then this angle here is also going to be theta, because these lines here that I have drawn, these horizontal lines are parallel lines, and then those two angles are corresponding angles, which means that, of course, if this is theta, then this is going to be a 90-degree angle, which means that this angle is going to be 90 minus theta, which means that this angle inside here is going to be an angle of theta, because I know that the angle made by this reaction force with the wall is a 90-degree angle. Okay, so if that angle is an angle theta, then if I look at the slope triangle that is going to be drawn, if I extend, for example, if I extend the line of NB, if I draw the slope triangle now, you will see that the slope triangle is now flipped. Okay, so if I draw the slope triangle here, this is going to be the following. It's going to be, hang on a minute, this is not necessarily coming out to be pretty nice to me. So if that angle is theta, then this angle also has to be theta. So this is going to be root 3, 1, and then 2. Okay, so as you can see, the slope triangle is flipped. So this is something you got to be careful, which means that if I am writing NB into its components, then the component in the horizontal direction is going to be the following. Okay, it's going to be 1 by 2 NB, and then the component in the vertical direction here, which we have drawn here. Okay, and then I'll clean up and then draw this figure again. This is going to be root 3 by 2 NB. Okay, so once again, I had the slope triangle here. This is a root 3, 1, and then 2 slope triangle. Slope triangle meaning that it's a right angle triangle, obviously. This angle is theta here, which means that this angle that I marked here is also theta, which means that I get this angle to be theta. Which means if I draw a slope triangle, then this angle also has to be theta within the slope triangle. Okay, and so my slope triangle, as you can see, has kind of flipped, and so I have to be careful in this particular problem for this one particular reason. Okay, so this is my free body diagram essentially, and if you want, you can clean it up and then do the other things here. I'm just going to go forward with what we are supposed to do. And what do I typically think of doing here? I have 3 unknowns, right? So what is my strategy? My strategy is, okay, hey, can I sum moments about a certain point and find one of the unknowns? Obviously, if I sum moments about the point A, I can find NB. Once I find NB, then I'm good to go, right? There is nothing much to do in this problem. Okay, so let me start off by saying, first of all, I have my coordinate frame. My x-axis positive, y-axis positive, and then counterclockwise rotations are positive. So this is x, this is y, counterclockwise rotations are positive. Okay, then I have the following, ax and ay, so they're not going to count into the picture because I'm summing moments about the point A and then setting it to 0. Okay, and then I'm saying all the counterclockwise rotations are going to be positive. So I do the right hand rule. Look at this, the 100 Newton force, a distance of 1 meter here, 1 meter for each of those, 100 newtons times the distance of 1 meter, that's a perpendicular moment arm, and it's going to cause a moment in the Counterclockwise direction. Use the right hand rule. Fingers of your right hand aligned with the force. Your palm is facing the point A. Okay, so this is going to be minus 100 times a distance of 1. The half NB force does not cause a moment because it passes through the point of interest. So the other force is root 3 by 2 NB force. Okay, so if I do that, that's going to be a counterclockwise rotation. And so root 3 by 2 NB, and then what is the moment or the distance from the point A to point B, perpendicular distance to that force, is going to be 2 meters. Okay, so times 2, this is equal to 0. So I solve for NB, and NB is approximately going to be equal to 58 newtons. Okay, and once I have NB, then the rest of the problem is just summing forces in the horizontal and vertical directions. As you can very clearly see, if I sum forces in the horizontal direction, let me do that next. Okay, so sum of forces in the x direction, all the forces pointing to the right are positive. Okay, what are the forces? I'm going to have a force AY which is pointing to the left, so that's going to be negative. Then I go back to my free body diagram. What are the other forces? A force of half NB which is pointing to the left, so that's also going to be a negative value. Okay, minus half NB, all of this put together is going to be equal to 0. Okay, so I already have a value for NB, so this is meaning that AX is equal to minus half NB. Okay, or AX is approximately equal to 29 newtons, negative newtons. Negative sign indicates that the direction we chose for AX was not correct, which is okay. There is nothing wrong with that. Okay, then I sum forces in the vertical direction and I set that all equal to 0. What are the forces in the vertical direction? Watch this carefully. AY is pointing up, positive. 100 newtons is pointing down, negative. Root 3 by 2 NB is pointing up, positive. Okay, so I'm going to collect all of these and then say, okay, AY minus 100 plus root 3 by 2 NB is equal to 0, which means that AY is equal to 100 minus root 3 by 2 NB, or AY, after you do the simplifications, is going to end up being approximately equal to 50 newtons. Okay, all right, and so this is the end of the problem. Essentially, I found out all the support reactions that are of interest to me, and a very brief recap. Okay, I go back to the problem here. There is a pin support at the point A. Okay, so this is an example of a pin support. Okay, a pin support at the point A, and pin supports typically prevent you from translating in both the horizontal and the vertical directions. Then I have a smooth contact at the point B, which means that this body is not allowed to travel perpendicular to the wall or perpendicular to the line of contact, which means there's going to be one reaction force there. So pin support, 2 reaction forces. Horizontal contact here, the line of contact is perpendicular, parallel to the wall, so the normal force is going to be perpendicular to the wall. So there's going to be one support reaction. You always want to make sure that if you have a two-dimensional problem for a single rigid body, you cannot have more than 3 unknown reactions. Okay, and so I draw the free body diagram. I choose the forces in any arbitrary x and y directions. NB, I know by the motion of the bar that the bar cannot move into the wall, which means that there is something resisting that motion, which means NB has to be pointing in the direction drawn. Okay, and then once I do that, then it's all about taking moments about the point A, and then I sum forces, and then I get all my unknown support reactions. All right, thank you very much.